Hello listeners, welcome you all. In this session, we will be discussing construction and classification of three-phase induction motor of the course of Principles of Electrical Sciences. I am Dr. Majid Jamil, Professor, Department of Electrical Engineering, Faculty of Engineering and Technology, Jamia Millia Islamia, New Delhi. So, here we will be discussing the construction of three-phase induction motor, classification of three-phase induction motor, and applications of three-phase induction motors. Three-phase induction motors are basically those motors which works on the principle of electromagnetic induction. In the three-phase induction motor, supply is three-phase input. The stator windings are connected to the three-phase supply, and so there are two main parts of a three-phase induction motor. One is stator and the other is the rotor. Stator is a stationary part and the rotor is a rotating part. Stator is an outer stationary hollow cylindrical structure made of laminated sheet steel. The laminations are slotted on their inner periphery. In these slots, a normal three-phase winding is placed which constitutes the stator winding. Stator is wound for a definite number of poles whose numbers depends upon the speed requirement. Greater the number of poles, lesser the speed, and vice versa. So, speed depends on the number of poles. If poles n is equal to 120 F upon P, speed is inversely proportional to the number of poles. If poles will be more, speed will be less. So, stator motors may be a 2-pole machine, 4-pole machine, 8-pole machines like this. So, this stator is shown here. It is a hollow structure. In the stator windings are shown here that are made of aluminium or copper bar, and the windings are placed in slots on the periphery of the stator. The other part of the induction motor is the rotor. Rotor is an inner cylindrical core built of laminated sheet steel strips with partially enclosed slots. The slots of the rotor are not always parallel to the slots of the stator, but they are given a twist known as skew. The rotor is known as skewed rotor. The windings of the rotor are placed in the slots. The rotor is mounted on a spider with a shaft. When properly assembled, the rotor is free to turn within the stator. So, the main parts of the induction motor, one is stator, the other is the rotor. Stator is a stationary part and the rotor is a rotating part. But in transformer, primary winding and secondary windings both are stationary. So, efficiency of the three-phase induction motor are less as compared to the transformer. As I mentioned, induction motors can be classified into two main groups: single-phase induction motor, three-phase induction motor. Similarly, three-phase induction motor can be classified further. One is squirrel cage induction motor and the other is phase-wound induction motor. So, three-phase motors is a classification of AC motor. The other type is synchronous motor and induction motor. Both are AC motor. But from construction point of view, in synchronous motor is also having stator and the rotor. Induction motor is also having stator and rotor. But the difference in the two is that the induction motor runs at speed less than synchronous speed and synchronous motors runs at synchronous speed. So classification based on the windings, based on the rotor winding. Three-phase induction motor we may classify it into two types. One is squirrel cage induction motor and the other is slip ring induction motor or phase wound induction motor. Classification depends on the design of the rotor circuit. Stator is same. So now we will be discussing squirrel cage rotor. As the name indicates, as this name indicates that the squirrel cage rotors are in design like squirrel. So it consists of a slotted laminated core of sheet steel. The slots of the rotor are not always parallel to the slots on the stator, but they are usually given twist known as skew. Each slot carries a thick copper or aluminum bar. These bars are short-circuited on either end by a solid copper or aluminum ring called end ring. The projecting rings and end rings are usually die cast in position. So this makes difference that the rotor circuit is short circuited. That is why they provides mechanical power. There is no electrical power in the rotor circuit. So squirrel cage induction motor construction is mentioned here. One is coil and the rotor coils are shown here in the figure. Slots are mentioned there. Shaft is there in center parts. Air gap is there. Windings are shown there. How it looks? Squirrel cage induction motor looks like this. So stator is there, center part is rotor, and then it is connected to the shaft. What are the advantages of squirrel cage induction motor? Its construction is very simple and rugged. And there are no brushes and slip rings. These motor requires less maintenance. Why less maintenance? Because there are no brush, there are no slip rings. That is why maintenance required is less. So most of the induction motors are squirrel cage induction motor. Reason? They are simple in construction. They are efficient. They are less maintenance required. So they performs better. Where they are used? Squirrel cage induction motors are used in lathes, drilling machines, fan, blowers, printing machine, etc. These are the applications of three-phase squirrel cage induction motor. The other type of induction motor is slip ring motors. The other name is phase wound rotor. It consists of a slotted laminated core of sheet steel. A three-phase winding is placed in the rotor circuits in the rotor slots having the same number of poles as the stator. The rotor winding is usually connected in star, though it may be connected in delta. Three-phase circuits may be connected either in star or it may be delta, but there are certain advantages of the star connections. That is why the windings are connected in star in most of the machines. The three free ends of the rotor windings are brought out and connected to the three slip ring mounted on the rotor shaft. Each slip ring is resting on a contact brush. So, in star connection, one end is common, the other three ends are free that are brought out. You will find here in the figure. The three brushes are further connected to a three-phase star-connected rheostats. This arrangement makes possible to include an additional resistance to each phase of the rotor at the time of starting. Thus, at the period of starting, additional resistance in the rotor circuit is included to have higher starting torque and when running under normal conditions. The external resistance are completely cut out from the rotor circuit and the rotor behaves like squirrel cage rotors. So, from this figure, it will be clear that the three ends of the star-connected rotor windings are taken out and they are connected to three slip rings through brushes. So, the rotor also carries star or delta winding similar to that of stator winding. The rotor consists of number of stators and rotor windings are placed inside these. It is shown here, slip ring induction motor. So, if we compare the two types of motors, slip ring induction motors and three-phase induction motor. However, first we will be discussing the advantages of slip ring induction motors. Slip ring induction motor has high starting torque and low starting current. Why? Because there is resistance in the starting circuit. That resistance, because of that, the torque becomes high. But due to the insertion of the resistance, losses will be more, so starting current will be low. Possibility of adding additional resistance is helpful in controlling the speed. Speed of the induction motor can be controlled by changing the resistance in the starting circuit. There are certain advantages of slip ring induction motors are used where high starting torque is required. Where are such applications? You have traveled in lifts, in cranes. So here starting torque required is high. So such motors are used in lifts, in elevators. So physically you can compare the two types of motor. One is squirrel cage induction motor, the other is three-phase wound motor. The top one is the squirrel cage and the bottom one is the slip ring induction motor. Comparison of two types of induction motors. Squirrel cage or slip ring. Speed is very important. So, of squirrel cage motor, speed is almost constant, but decreases slightly with increased in load. But in slip ring induction motor, speed decreases with load more rapidly than the squirrel cage induction motor. The other important parameter is torque. Starting torque is somewhat less of squirrel cage induction motor, but running torque is good since most of the time we require the running torque. So, squirrel cage induction motor, in most of the industries, you will find squirrel cage induction motor since the torque is good for squirrel cage induction motor. However, in case of slip ring induction motor, the starting torque is about 3 times the full load torque, but running torque is also good, but not as good as in case of squirrel cage induction motor. The other parameter is the current. Starting current in case of squirrel cage induction motor is about 5 to 6 times of the full load current, which is undesirable. But in case of slip ring motor, starting torque is less. It draws hardly 2 times the full load current. So this is the better in this case. Next is the speed control. Speed control of induction motor or of any type of motor is always an important consideration. Speed control should be in our hand. It should be easily controllable. So, in induction motor, speed control is not as easy as in case of DC machines. But in case of induction machine, in case of squirrel cage, this is done by changing the poles. As I mentioned, speed is n is equal to 120 F upon P. So by changing number of poles, we can change the speed, but changing pole is not easy because the construction, at the time of construction, number of poles are fixed. But some arrangements can be made for change the number of poles in the stator winding. So speed control is possible, can be done, but not as good as in case of DC machines. In case of slip ring induction motor, it is done by changing external resistance of the rotor circuit. The power factor is another important parameter. In case of squirrel cage induction motor, power factor is low. In case of slip ring, power factor is high. Cost of squirrel cage induction motor is low because there are no slip ring, there are no brushes, they are simple in construction, they are compact, so cost is low. However, as compared to the squirrel cage induction motor, the cost of slip ring induction motor is higher. Now, another thing is maintenance. So, maintenance of squirrel cage induction motor is low and slip ring motor is high. Why? Because in squirrel cage motor, there is no slip ring, there is no brush. In case of slip ring motor, there are slip ring brushes, so maintenance become high. Applications, I have already mentioned, they are used in lathes, drills, printing machines, blowers, where a constant speed is required. Squirrel cage motors are used. But in slip ring motors, where high starting torque is required, that is lathes, lifts, cranes, elevators. So the slip ring motors are used in such applications. So we have discussed here the construction of three-phase induction motor, comparison of the two types of rotor, squirrel cage and induction motor, concept of slip, concept of rotor speed. So based on this, we will be discussing a numerical problem. A 208 volts, 10 horsepower, 4 pole, 50 hertz induction motor has a full load slip of 5%. So, what is the synchronous speed of this motor? So, what is synchronous speed? It is Ns is equal to 120F upon P. So, frequency is 50 Hertz. Number of poles are 4. So, synchronous speed is 1500 revolution per minute. This is the synchronous speed. The next part is what is the rotor speed of this motor at the rated load. So, the rotor speed of the motor is N is equal to 1 minus S over Ns. Since in this case, slip is 5%, 5 means 0.05. So, rotor speed, which is also called the motor speed, so motor speed is 1 minus S into Ns. So, the speed of the motor is 1425 revolution per meter. If you compare the two speed, one is synchronous speed and the other is the motor speed or rotor speed, there is a difference. So, this difference is called the slip. Induction motor cannot run at synchronous speed. So, that is why the speed of the induction motor is always less than synchronous speed. So, a motor running at 50 Hertz supply having 4 poles, so if synchronous speed is 1500 RPM, so that will rotate at 1425 revolution per minute. This is the speed of the motor. This is the speed of the rotor. What is the rotor frequency of this motor at the rated load? Rotor frequency, one is supply frequency, 50 Hertz. Rotor frequency will always be less than 50 Hertz. Rotor frequency of the motor is given by R is equal to S into F. F is the supply frequency, or we can call it Fe. So, slip is 5%, supply frequency is 50 Hertz. So, rotor frequency is 2.5 Hertz. Alternatively, the frequency can also be found from the slip formula. Fr is equal to P upon 120 Ns minus N. So, here also the rotor frequency is 2.5 Hertz. So, the next part is the shaft torque of this motor at the rated load. The shaft torque, power is torque into speed. So, torque is power output upon rotating speed. Since motor is of 10 horsepower and 1 horsepower is 746 watt. So, shaft power in terms of watts will be 7460. A 10 horsepower is equivalent to 7460 watts. And the speed we just calculated 1425. So, the torque with this is 50 Newton meter. The torque of the motor is 15 Newton per meter. So, this problem is giving a clear idea about synchronous speed, speed of the rotor, speed of the motor, and the torque of the motor. So speed of the motor is always less than the synchronous speed. Move to the next problem. A three-phase induction motor is sometimes called a generalized transformer. So here we will discuss how a three-phase induction motor operates under the following conditions. Number one, rotor frequency. If frequency of the rotor is same as the stator frequency, if the frequency of the rotor is less than the supply frequency, if the frequency of the rotor more than the supply frequency. So this frequency concept in transformer, frequency remains constant. In frequency of the input power, frequency of the output power, voltage of the output secondary winding, voltage of the primary winding, frequency remains constant, because the primary winding and secondary winding in the transformer are stationary. But in three-phase induction motor, primary winding, which is stator winding, it is stationary. But the secondary winding, which is the rotating winding, that is rotating part, which is rotating at some speed. So frequency of the rotor circuit, frequency of the generated EMF in the rotor circuit, frequency of the current in the rotor circuit will be different from the frequency of the supply. So here frequency of the supply is F is equal to Pn upon 125. So frequency of the rotor induced EMF is P by 120. P is the number of poles on the stator. If number of poles are equal in the stator and in the rotor, then what will be the frequency? When rotor is stand still, so frequency will be the same in the rotor circuit as of the supply frequency, as it happens in the transformer. But when supply frequency is more than the rotor frequency, then motor is running under normal conditions, which is the case it should be. The third part, when frequency of the rotor circuit is more than the supply frequency. Supply frequency is 50 Hz. If frequency is more than 50 Hz, then the rotor is driven against the direction of the rotating field. Then rotor generated voltage and rotor current is maximum when the rotor is stand still. Rotor EMF and the rotor current are zero when rotor is at synchronous speed. Both E2 and I2 are minimum at no load. So slip is negative when induction motor works as induction generator. When it will be? When rotor will be moving faster than the synchronous speed. So in that case, our induction motor will behave like an induction generator, and instead the direction of the current will be reversed and it will supply the current. It will not draw the current, it will supply the current. So the same motor will work as the generator when speed of the motor is more than the synchronous speed. So in this module we discussed the construction of induction motor, the two parts basically stator and the rotor, and then classification of induction motor, and classification depends on the design and construction of the rotor circuit. Stator is common. So, squirrel cage induction rotor or phase wound induction motor. Phase wound induction motor is also called slip ring induction motor. So, there are certain advantages where constant speed is required. We use squirrel cage induction motor. Squirrel cage induction motors are simple in construction, require less maintenance, they perform better, their efficiency is good, they are economical. And phase wound rotor motors, where variable speed is required, high starting torque is required, like in cranes or lift, phase wound motors are used, but they are little expensive. So, in this modules, we have discussed construction and classification of induction motors and their applications. Thank you, viewers. Now it is over. Wishing you all the best.